Ants have evolved a variety of behavioral, physiological, and structural adaptations to survive cold weather, a challenge they face in most parts of the world. As ectothermic creatures, organisms that rely on external sources to regulate body temperature, ants cannot produce their own body heat, making it essential for them to adopt effective survival strategies when temperatures drop. With a range of tactics like clustering together, burrowing deeper into the ground, altering their metabolic rates, when temperatures fall, ants begin preparing for winter by adjusting their daily routines and changing their physical environments. During late summer and early autumn, worker ants collect food to build up the colony's reserves. Many species focus on gathering fats and carbohydrates, which provide long-lasting energy. These food stores become critical as winter approaches because food sources become scarce and colonies often rely on stored food to sustain themselves throughout the colder months. As temperatures continue to drop, ants will begin to retreat from the surface. A common strategy among ants is to burrow deep underground, where the earth acts as an insulator. Deeper soil layers stay significantly warmer than the air above, especially during winter. By moving several feet down, ants can avoid the freezing temperatures above ground. Some ant species dig even deeper than others, forming intricate tunnels and chambers that reach depths where soil temperatures remain relatively stable year-round. Within these deep nests, ants establish chambers specifically designed to hold food and support the colony's survival needs. Once the colony is secure underground, ants enter a state of dormancy to conserve energy. This dormancy is not the same as hibernation seen in mammals. During diapause, ants consume less energy, allowing them to survive extended periods without regular access to food. Their movements slow, and they become less active, which reduces the need for frequent feeding and further conserves the colony's food reserves. This strategy enables ants to remain in their sheltered nests without expending much energy. One crucial factor aiding in ants' cold tolerance is their ability to produce specialized proteins and chemicals, known as cryoprotectants. Social insects, ants rely on cooperation to overcome challenges that would be insurmountable for solitary insects. This tactic is especially effective in conserving warmth and helps reduce the risk of any one ant freezing to death. In fact, clustering behavior is seen not just among ants but also in other social insects like bees. The ants' ability to collectively adjust to the environment by creating these heat pockets exemplifies how social behavior is crucial to their survival strategy. The structure of the ant nest is another significant factor. Ants build their nests with materials that provide natural insulation, such as soil, sand, and plant debris. In some cases, ants line their nests with small rocks or cover entrances with loose particles to block cold drafts. Some species even construct complex networks of chambers at various depths, which enables them to move to warmer or cooler sections as needed. The design of their nests allows ants to control exposure to temperature fluctuations and maintain a more stable microenvironment. Furthermore, in regions with exceptionally harsh winters, certain ant species will create temporary closures to their nest entrances using plant material or soil. This behavior reduces the inflow of cold air and prevents predators from entering the nest during this vulnerable period. This behavior results in larger clusters of ants, which generate and retain more warmth. Honeydew, rich in sugar, provides a vital energy source that supplements the ants' stored food. In regions where winters are less severe, ants employ slightly different strategies. For example, in temperate climates, ants may enter a lighter state of dormancy called quiescence, where they remain somewhat active and can venture out if conditions allow. These ants may be found foraging on warmer winter days, taking advantage of any accessible food sources. remaining dormant only during the coldest periods and resuming activity whenever temperatures rise briefly. This strategy allows them to replenish food supplies and maintain their colony without fully relying on stored resources. Ants' physiological and biochemical responses to cold also reveal the species' adaptive complexity. These lipids ensure that cell membranes retain their function at low temperatures, preventing the cells from becoming too rigid and maintaining essential processes even during cold exposure. Additionally, the composition of these lipids is adjusted in response to seasonal changes, increasing resilience during winter. The role of fat bodies, which are specialized tissue structures in ants, is also crucial during winter. Fat bodies store lipids, proteins, and glycogen, serving as energy reservoirs that can be metabolized slowly over time. In winter, these fat bodies become a primary source of energy. The reserves stored within the fat bodies are usually sufficient to last through the colder months until spring, when food becomes readily available again. Interestingly, certain ant species have evolved even more specialized adaptations to endure extreme climates. For example, the winter ant, Phrenolopus imperus, commonly found in colder parts of North America, has a unique physiological response to cold. These ants are capable of foraging at temperatures just above freezing and can resume activity in early spring, before other species are active. Their tolerance to cold is significantly higher than that of many other ants, and they thrive in climates where other species cannot survive the winter. This adaptation gives the winter ant a competitive advantage in colder environments, allowing them to occupy ecological niches that would otherwise remain vacant during these periods. Ants' survival in cold weather, while fascinating, underscores the delicate balance of their ecosystem. Their winter survival strategies not only demonstrate their resilience, but also highlight the interdependence within ecological communities. By surviving winter, ants maintain their roles in food webs, soil aeration, and seed dispersal, ensuring continuity in the ecosystems they inhabit. Their complex responses to cold climates reflect millions of years of evolution, during which ants have developed a suite of adaptive responses. In summary, ants' ability to survive cold weather is the result of an intricate blend of behavioral, physiological, and structural adaptations. By storing food, burrowing underground, entering dormancy, producing cryoprotectants, clustering together for warmth, adjusting their nest structures, modifying diets, and employing unique interspecies behaviors, ants demonstrate remarkable resilience to winter's challenges. Their adaptations enable them to conserve energy, prevent cell damage from freezing, and ensure the survival of their colonies until warmer conditions return. Through these strategies, ants have mastered the art of winter survival, showcasing the incredible resourcefulness and adaptability of these small. Thanks for watching. Subscribe for more.